Hello, everybody. Good morning, and welcome to our virtual lecture series today. So, my name is Mark Bernardes, and I'm the Communications and Marketing Officer for the Department of Chemical Engineering at UCL. And today we are running a Spring into STEM, the World of Petrochemicals virtual lecture series by Dr. Les Bolton, who's with me today. The session will be recorded and shared with you all afterwards, and will be made available on YouTube. If you do have any questions throughout the session, do pop them into the Q&A box at the bottom of your screen, and Dr. Les Bolton will be answering your questions, and I will also be assisting. At the end of the session, there'll be an opportunity to complete a feedback form. And that will just help the department in improving our sessions. So without further ado, I'm going to pass you over to Dr. Les Bolton, and he will be presenting this lecture today. Thank you.
Thank you, Mark. Good morning, everyone. I should probably start by giving you an introduction of what I'm aiming to do over the next hour or so. So what I'm going to try to do is to give you as potential prospective chemical engineering students a bit of an overview of what the petrochemical industry is, explain what it does, look at the main things that it makes, what they do, and why they've become so widely used, look at a few of the major processes that are in it, try to put some context on the scale of the industry, and look at the roles of chemical engineers within the industry. I'll also have a quick look at some of the sustainability challenges that the industry faces and what essentially the industry and society's options are as we try to seek a more sustainable future. And I do this because I think it's important to understand the complexity of the petrochemical landscape to get hold of the scale of the challenge of trying to replace it or reinvent it. Okay, my background. Well, I did an MEng in chemical engineering at Cambridge and a PhD a long time ago. And I did a PhD specialization in hydrodynamics of fluidized beds. And that was done sponsored by British Gas, because they were trying to scope out routes to coal-derived substitutes for natural gas. And those were, it seems a long time ago now, because nobody knew anything about anthropogenic climate change in those days. The view was that coal was the future. Very interesting how the world has changed. I joined BP in 1987 after completing my PhD, initially up in Grangemouth in central Scotland at the Petrochemicals Research Centre, which is now part of INEOS, as a specialist engineer doing modelling, that is, predicting by computer calculations of the science and underlying effects how processes would perform. After that, I got involved on the manufacturing side, developing and implementing advanced process controls, which are how you make the process do what you want it to do, and operator training simulators, which I guess nowadays we would call them a digital twin, but they've been around a long time, where you have a mock-up that looked exactly like a plant control room, but a computer behind it doing what the process would do. I then moved down to the main corporate centre in Sunbury as a specialist engineer, and I covered a great range of topics over the years until I took early retirement last year. I'm also active in the IChemE. I chair the Education and Accreditation Forum, which essentially is about ensuring that university courses meet the requirements educationally for chartership. Okay, so what's the petrochemical industry? Well, you'll have heard of an oil refinery. An oil refinery takes crude oil and makes things like gasoline, diesel, kerosene, various fuels out of it, and coke. So its products of refinery are fuels mostly, and then mixtures. There is a stream out of the refinery that we tend to call naphtha, which goes onto the petrochemical works. And sometimes we make petrochemicals from natural gas as well. But essentially, a petrochemical works makes single chemical species, particularly polymers. So things like ethylene and polyethylene, propylene and polypropylene, all those sorts of things. Okay, so quite distinctive from the oil refinery in its role. And I should perhaps say it's very common in the petrochemical industry to use the historic, old-fashioned, non-systematic names. So the industry still says ethylene and propylene. It doesn't say ethene and propene. It says paraffins and olefins. It doesn't say alkanes and alkenes. People within the industry learn it really quickly. I wouldn't worry about it. But yeah, so some of the labeling I will use in this talk may be a bit unfamiliar to you. Okay, complexity. When we talk about polyethylene, which you may think of a polythene, polythene is an ICI brand name when the product was very commonly used in the 60s and 70s, it sounds like we mean a single product, but actually it's much more complicated than that. The original polyethylene was discovered by accident by a couple of chemists working for ICI, and they were doing some high pressure experiments on ethylene, which is a gas, and they found a waxy solid deposit, which initially they didn't really understand. They worked out by analysis that it was a polymer, and that is what we now call low density polyethylene, and it was what ICI called polythene. It's still made today. It uses high pressure reactors at 2,000 to 3,000 atmospheres. So that's quite heroic engineering, if you like, having processes that make those conditions. And what they do is they link the ethylene in a random structure, which gives you a material with limited strength. So it's useful for things like plastic films, food packaging, etc. About 20 years later, another chemist in Germany discovered a process which links the ethylene together in a different way, in straight chains without branches. And that makes a much harder, much denser material that we call high density polyethylene. And that's useful for making things like gas and water pipes. And then later developers found a way of copolymerizing a small amount of molecules like butene and hexene in to control the number of short branches on those linear polymer chains to make linear low density polyethylene. And that's something you can use for the same things as conventional low density polyethylene, but it's stronger, so you can use less of it. Now, polyethylene is the largest tonnage polymer produced, but there's lots of others that we call collectively polyolefins, based on linking together molecules in double bonds. So things like polypropylene, really tough polymer used for things like carpets in high wear areas and car bumpers. So polypropylene carpets you might use in an office. You probably wouldn't use it for a bedroom because it's too rough. Polybutenes, polyalpha olefins, viscous liquids in lubricants. Polyvinyl chloride is resistant to degradation by ultraviolet, so we use it for outdoor items like window frames and doors and drain pipes and gutters. And polystyrene, clear, rigid polymer used for things like disposable tableware and CD cases. So I think you're starting to see there's actually a very wide range of different materials in this single class. But then there's another entirely different group of polymers that was discovered by a scientist, chemist at the DuPont company in the 1930s, just after polyethylene was discovered. And that was made by reacting two different molecules together. And the first example was nylon, which is called a polyamide. And that takes amines, reacts them with carboxylic acids, that should say, not carbonylic acids. So an amine like that one, top right, amine groups at two ends of a chain, carboxylic acid groups at two ends of a chain. The acid groups can't react with each other, the amine can't react with each other, but an amine molecule, an amine tail can react with a carboxylic acid head. And so you would create a chain of alternating segments. The most common polymer of this group now is polyethylene terephthalate, PET, and that's a polyester made by reacting terephthalic acid with ethylene glycol. And here they are, terephthalic acid. Again, it's the same kind of idea. You've got a molecule with two carboxylic acid groups at the end. Ethylene glycol has got OH groups at the two ends. These can react. these can cross-react but not react with themselves. And again, you make a long chain out of it. And PET, we all know very well, it's the polymer used in textiles, polyesters, and is very widely used in drinks bottles. And it's even more complicated than that. Even within single polyethylene types, there are different grades or specifications for different purposes. And that's awkward because it limits how useful simple mechanical recycling can be, because any mixture is going to have hugely inferior properties to the stuff you started with. The other thing is, other stuff gets mixed in. Plasticizers are added to make a material easier to process. There are things like fire retardants, colorants added for some purposes, which makes a really complicated landscape. And you need to think about that for developing any recycling technology. And we'll talk about that a bit later. Okay, next we're going to have a look at some of the processes used in the petrochemical industry. And probably the most important single one is called steam cracking. And this is what you use to convert the raw materials, the naphtha or the natural gas, into reactive intermediates, ethylene, propylene. And the key thing is these molecules, ethylene and propylene, have double bonds in. The double bonds allow you to do reactions relatively easily, and so those are what you can make complicated chemicals out of. So in steam cracking, you take something really unreactive like ethane, propane, or other alkanes, and you really roast them. You react them at very high temperature in tubes in a furnace to make these reactive intermediates. It's an endothermic process. By that we mean you have to put heat into it to make it happen. Whereas the things that you then do with those intermediates are usually done at much lower temperatures, 100 to 300 degrees C. And most of those are exothermic, heat is given out. So you're putting heat in at really high temperature and you get some of it back at low temperature. Steam cracking processes are really complicated because you have to do the reaction really hot. It makes economic sense to have a way of recovering that heat as much as possible and using as much of it as you can. Because the products are reactive, the mixture you get out of it is really complicated. Effectively, it contains just about every possible hydrocarbon structure you could create with between 5 and 7 carbons, depending on how hot you do the reaction. And so you end up with a really complicated separation system. So these are the core planks of chemical engineering, if you like. How do you do a reaction? And then how do you separate the products you get from that reaction and clean them up? And how pure does it have to be? Well, the ethylene that you use to make polymers typically needs to be over 99.9% pure. So you have to purify to a really high degree. Because the products are like gases, the separation also needs to have sections at really low temperatures, as low as minus 145 degrees C. So you've got a process that takes your feedstock up to maybe 800 or 900 degrees C, and then a few seconds later, the same material is down at minus 145. Quite severe and dramatic engineering. And just about everything you can learn in chemical engineering, you put into practice on a steam cracking plant. It's got all sorts. Petrochemical processes are most economic when they're operated at really large scale. And I think you can think of the principle of this, if you imagine a tank of material, if you double the diameter, the amount of material you need to make it goes up by a factor of 4 because it depends on the surface area. But the amount of volume goes up by a factor of 8. So you can see if you're dealing with tanks and vessels, increasing scale means you need less metal to build it. So large is usually economic. So I think there are 4 steam crackers in the UK, each of them making between 700 and 800,000 tonnes a year of ethylene and substantial amounts of other materials. Most crackers in Europe are similar sort of scale. There are some larger ones in the Middle East and China. Ethylene and propylene, because they're gases, are quite expensive and difficult to transport. So what you normally do is you put a collection of plants making derivatives which are not gases adjacent to your cracker. And those derivatives are typically making an order of magnitude less material. And different plants will have a different combination of derivatives. So a different combination of polyethylene, polypropylene, and other chemicals that you can make from each of them. For some context, I weighed some thin carrier bags from a supermarket, and a carrier bag weighs about 10 grams. So 100,000 tonnes a year is about 3,000 tonnes a day. In other words, 300 million carrier bags a day. So that's a huge amount of material. I'm not suggesting for 1 minute that those plants are making stuff that is entirely making carrier bags, but that gives you a context of how much polymer is manufactured. Okay, what does a steam cracking plant look like? So this is a picture of the steam cracking plant at Geleen in the southeast of the Netherlands. And I'll try and walk you through it. So you can see a person standing there in the red boiler suit. Okay, this is a furnace. If I pull a box around it, so there'll be burners in here firing into this big box, which is basically a metal box with refractory on the inside to keep the heat in and to protect the metal. The cracking tubes with the reaction are in here somewhere. And then you'll see a lot more equipment up here. So what's necessary from this furnace is then to have lots of surface area to generate steam with the flue gases that come up here and eventually comes out to a chimney. And you can see there's 1, 2, I'm not sure what this box is for, 3, 4, 5, 6 furnaces. And that's pretty normal. So you have 6 furnaces doing maybe 100 to 150,000 tonnes a year. And there'll be an entire separation section somewhere else. So that gives you an idea of the scale. Person, truck, furnace. Next slide is what a polyethylene plant looks like. And this is typical of a polymer plant. And this is very similar to one that I worked on, well, several that I worked on in my early career. So there's the reactor, there's the reactor, this shiny metal vessel, typically about 5 meters diameter down here. It broadens at the top because you've got gas flowing upwards through here, a bed of powder, and widening it means the gas slows down and the powder doesn't get blown out at the top through this pipe. And typically 20 to 25 meters tall. And that should be enough to make at least a couple of 100,000 tons per year. And then you'll typically have silos to store the product. So that's what it looks like. So why do we use these products? Well, petrochemical processes produce a huge array of materials, mainly polymers that we use in modern life. And we use them really for 2 reasons. One is they perform much better than many other materials in certain jobs. They generally last longer than most alternatives. They don't biodegrade, they don't rust, they do deteriorate with age. If anyone has found an old plastic bag in a cupboard and see what state it's in, they'll realize it does deteriorate because the plastic crystallizes slowly. Plastics are generally much less heavy than alternatives like glass or steel. So I weighed a half-litre beer bottle. It weighs about 300 grams compared to the contents of the beer about 500 grams. Whereas a 2-litre plastic milk container only weighs about 30 grams. So using that very light material reduces your transport costs and therefore reduces your energy consumption. So that's a good thing. Plastics are also resistant to gas diffusion. So thin films of plastic extend the shelf life of food. Synthetic textiles are hard wearing and water resistant, and we are used to a large part of our clothing being made from synthetic fibers. They're also incredibly cheap to produce. So polyethylene, for example, costs about £1,000 per tonne to make. So the cost of materials in a supermarket carrier bag is about a penny, which is actually, in a way, a problem, because you can imagine if the material in a carrier bag is only worth about a penny, it's quite difficult to make an economic recycling process. Okay, so we all know now that these products come at an additional environmental price. There's a significant energy consumption in the manufacture of them and the consequent CO2 emissions. So you think of the fuel it takes to fire those furnaces that I showed you. We know that waste plastics do not biodegrade easily. And a challenge we have is how we reduce our dependence on plastics, how we get rid of wasteful usage, and how we properly manage the waste that we necessarily create. And I'd say the challenge for chemical engineers working with other technologists such as chemists and material scientists and other engineers is to create the viable alternatives. At the moment, in a lot of situations, it is quite difficult to see what the alternatives are. So what do we want to achieve in terms of sustainability? Well, again, this is one of those things which is quite easy to be vague, but in plastics, I think we need to be very clear. Here are some different sustainability objectives we might want to achieve, and we probably want to achieve all of them in some circumstances. We may want to reduce depletion of scarce resources. It's an important thing. We may want to reduce the energy consumption or the CO2 emissions, both in the manufacture and the usage. We probably want to reduce waste. We'd like to recycle products. We'd like to avoid non-biodegradable waste. So all good things we want to do. How do we prioritize between them? In some cases, they conflict with each other. It's not as simple as you might think. Nobody wants a biodegradable water or gas pipe underneath their house. So clearly that's a situation where you don't want biodegradability, you want permanence. There's a significant carbon footprint for making plastics and using them. But in a lot of cases, it's less than a lot of the alternatives, whether it's paper, cotton, glass, or steel. And carbon taxes are therefore very unlikely to make us use other materials instead of plastics. They might change the way in which we make plastics. So there's a piece of research I'm referencing here from Northern Ireland Assembly that reckoned it takes 4 times as much energy to make a paper bag as a plastic bag. And that feels about right to me, because you think about how paper is made. Essentially, you chop down a load of trees and you cook them in caustic soda for a long time, in sodium hydroxide, to make the pulp for making paper. So those are quite energy consuming processes as well. But that's just one of the aspects. The paper bag, of course, is biodegradable. The really distinctive issue with plastic, I think, is how you deal with the waste. Some uses of plastic, as I say, the lack of biodegradability is a good thing. For most uses, dealing with the waste is the most intractable problem that we have. And again, there's been a lot of thought about a lot of awareness in the last few years about where plastic waste ends up and how it's handled. Okay, so how do we recycle? How can we reuse plastics? These are the topics that we're starting to look at across the industry now. So this is a nice little diagram that CEFIC are the European Petrochemical industry organization. They've produced this diagram of different options of how you can reuse and recycle plastics. And essentially, the smaller the loop you go around, the better. So your plastic product, you use it, that might make plastic waste, and historically that's been disposed of. And we would get new plastic from fossil resources going to a feedstock, going to a monomer, ethylene say, and a polymer, and being made into products. Clearly, reusing stuff is always going to be the most efficient option. But the next most efficient thing is going to be mechanical recycling. In other words, you just melt down the polymer, make it into new products. But as I think I mentioned earlier, that only really works when you've got clean, unmixed single polymers. For example, clear drinks bottles, those would work. The three options at the top are where there's a lot of work for chemical engineers in terms of new process development. So one which I think is quite a niche one is dissolving polymer in a solvent to extract one polymer from a mixture. So there's quite a neat technology that a company called Clariant have developed, which essentially is an alternative carpet backing material. So instead of having this sort of latex foam that's currently used, their material could be dissolved off and reused. And I've given a link there to their website that gives some more information on that. That's one example, but I think that's quite a niche example. There are not many polymers like that. One which is more widespread and becoming more heavily looked at now is depolymerization. So you take polymers and break them down into the intermediates that were made out of. Now that's an option for things like the condensation polymers, polyesters, polyamides. It doesn't really work for polyolefins. So an example of that are INEOS, who are developing a technology called Infinia for depolymerizing polyester that's not suitable for mechanical recycling. So yes, if you've got a lemonade bottle and can separate off the label and the cap and so on, that you can mechanically recycle. But if you've got a polyester carpet or polyester clothing where it's mixed up with all sorts of other stuff, you can't really do that. And so this is an option for that. And the issue here is how you deal with the impurities, how you deal with the other polymers that get mixed in. Can your process handle it without getting fouled up, without getting deposits all over it? The most severe one is what's labeled on here as conversion. So that's taking the polymers at high temperature, either through pyrolysis, in other words, just heating, or gasification, which is where you react with some steam and oxygen to make mixtures of carbon monoxide and hydrogen. Essentially, they're going back to really raw feedstocks. So you have to put another step in the chain. Effectively, you have to put the steam cracking step back in. That's the only option that really works for mixed polymers. And there's lots of companies involved in those sorts of technologies. But I'd stress that the bigger this cycle, and this piece of the cycle, particularly conversion and remaking from feedstock, is pretty energy intensive. And so you don't want to do it unless you have to. There's two other things you can do. If you're doing these pyrolysis type processes, you could actually turn this feedstock into other things like transport fuels. But then, of course, you're going to emit CO2 from the combustion of those. Or you can use them as a fuel to generate power. That's often called waste to energy. So some observations on recycling plastics. You'll recall that I said plastics are really, really cheap. And that means you have to have a very efficient way of collecting and segregating those waste plastics. Impurities really matter a lot. Now, sitting on my desk, I have a lemonade bottle, which is made of PET, but it's got a cap. The cap almost certainly isn't made of PET. It's got a label. The label also is almost certainly not made of PET. So if you put that in entire, then all of those impurities get in, and those will foul up the sort of process that works by dissolving and depolymerizing the plastic. You may have seen in recent years, some companies are producing water bottles with slightly unusual caps, which are made of the same material. So that's the kind of development that companies are looking for to make things more recyclable, reduce the number of different polymers in any given object. I think I've just said that. Chlorine. Chlorine is a real problem. Chlorine, which you can get from PVC, and even tiny amounts of it, can be really damaging to processes. So chlorine, for example, is highly corrosive, and so your steel pipework is in danger from the chlorine release. But chlorine also damages catalysts, tiny amounts of it, parts per billion of chlorine will destroy a catalyst in weeks. The other thing is, because of the cost or the value of the polymer, the processes will have to be extremely efficient users of energy, especially heat. Because if a recycling process has a higher carbon footprint than making new polymer from scratch, then actually doing waste to energy will be effectively a reduction in carbon emissions. Okay, so you have quite a low threshold on how, it has to be, sorry, a high threshold on how efficient you have to be. So as a result, all of these processes have complex chemical engineering. A lot of work goes into reactor design, and there's a lot of work needed on separation and purification systems. Going to have a few slides on biopolymers and bioplastics as one of the other routes that companies have taken. And first, a warning that the words mean, very confusingly, two entirely different things. Sometimes people use the words biopolymers and bioplastics to mean plastics and polymers made from renewable, in other words, biological feedstocks. And sometimes they use them to describe biodegradable plastics and polymers. You can, of course, have polymers which are both. So some biopolymers, such as polylactic acid or PLA, are biodegradable. But you can, in principle, make PLA from a fossil feedstock. Nobody does, it doesn't make sense, but you can, in principle. And some conventional polymers, like polyethylene, can be made from renewable feedstocks. And the use of both of those is growing, but it's still tiny compared to the general market. Several manufacturers now make polylactic acid, and you do it by fermenting sugars to make lactic acid, and then you polymerize the lactic acid. PLA is being more widely used in various packaging now, so it's biodegradable, industrially compostable. It will take a long time to break down in a garden compost bin. Industrial composting, which is done hotter, tends to work better. And manufacturers are still working on improving its barrier properties for use in food packaging. It's not as effective as polyethylene at keeping food fresh. And they're also working on its strength. And you may have seen it used to do bulk mailing wrappers. In the bioethylene space, Brazilian company Braskem commissioned its first bioethylene plant in 2010. So essentially it takes sugarcane, converts it to ethanol, and then ethanol to ethylene. And it produces some biopolyethylene from it. It's identical to fossil-based polyethylene. It has a substantially lower carbon footprint. It can, in principle, be used for any polyethylene application. I think the one that's gained the most attention is, if you know the little green trees in a Lego set, those apparently are made out of biopolyethylene. And you can only tell the difference by carbon-14 dating, because carbon-14 dating will tell you about the age relative to the atmosphere of the material, of the carbon that's in the product. There is a newer technology that's not been commercialized yet that I have to mention because I was involved in it, which is Technique's ethanol to ethylene technology called Hummingbird. Okay, another biopolymer example is PEF, polyethylene furanoate. It's a plant-based alternative to polyester. One of the intermediates can be made from forestry waste or agricultural crops. and the other can be made from bioethylene. But researchers are working on other routes. And in principle, it can be used for the same things as PET, plastic bottles, fibers, etc. But it's currently much more expensive. And so any manufacturer would need a good reason, good incentive to use those bottles. And it's not biodegradable. There are also routes to PET from biological feedstocks, which therefore compete with PEF. So, for example, an American company called Virant has a bioforming process which takes carbohydrates and makes a mixture of hydrocarbons with it. And you can use those hydrocarbons either as biofuels or chemical feedstocks. And the main chemical feedstock they're targeting is paraxylene, which is the feedstock for making PET. Again, not yet commercialized. Advantages and disadvantages, well, businesses that use PET will be reluctant to take a similar but slightly different material because they need to modify all their equipment. The PEF route is likely to be simpler than biologically derived PET, so there are different places in the chain of manufacture that are simpler and different places that are more complicated. And it's not clear yet which is likely to be more successful. So, some closing thoughts. A lot of complexity. I've given you a huge amount of information in a short time. Petrochemicals, particularly plastics, do lots of jobs that are not easy to do with other materials. It's not obvious always what the best way is to reduce the environmental impact. There is going to be a continuing need for some really radical innovation to come up with alternatives that improve sustainability in different ways. There are huge opportunities for chemical engineers working with chemists and material sciences in developing and commercializing new technologies. And I would say don't underestimate how difficult the transition is going to be. We've got a lot of focus on plastic bags in the last few years, but there's actually a huge amount of other plastic out there in our society. And switching plastic, say, to glass or steel or aluminium has other consequences. Bioplastics are very much in their infancy, and I suspect that oil and gas will carry on being used to make plastics long after we stop using them as fuels. I suspect quite a few of you may end up working in the conventional petrochemicals industry. I would say that is a fantastic learning ground. There's a huge range of processes and using almost every imaginable aspect of chemical engineering. And one side benefit of this need to improve sustainability is it brought a new wave of innovation and opportunity. When I started my career back in the late 80s and early 1990s, it almost felt that we were close to the end of the innovation chain. We had all of the processes we needed. They were all quite efficient for what they did. But now it's clear that we actually need a huge range of new things that are different. And so that creates great opportunity and creates a really exciting place to work. So I'm going to leave it there. Thank you all. And I think I now need to go to questions. So I think I'll stop sharing my screen. And I'll go to Q&A. Right, so let's try and go through these questions. Difference between polymers and plastic. Well, strictly speaking, plastic is a word that it's the word for the mechanical properties, and some of the early polymers were called plastic because people thought they were plastic. Actually, within most of the range of operation, they're not. They're elastic. If I take this bottle and squeeze it, well, you can't see it because of the clever background. If I take the bottle and squeeze it, it bounces back. So it's clearly not plastic, it's elastic under the definition you've got in physics. So plastic is a bit of a common parlance word rather than the real word. They're polymers because they're made from building blocks. Some environmentalists are against plastic. Which are more acceptable? What are the drawbacks? Well, I think What I would say is that I think we need to be sensible about the usage. I think very durable plastics like the sort of things we use for gas and water pipes or for window frames and doors and so on, that seems to make sense to me. I think we need to find a better solution to packaging and reduce the amount of it we use. Do these plants require offshore work? These will all be onshore. The feedstock may come from offshore in some places, but these will all be onshore plants. You don't build things offshore unless you have to. What are the innovations and frontiers of research for petrochemical today? Well, I think it is mostly in these alternative processes, either from biological feedstocks or making sustainable products. I think those are the main areas of use, the main areas of focus. Ooh, 3 questions. Did I make a conscious decision to stay with BP throughout your career, and why? Well, I had an interesting one about 15 years ago, which is when BP decided to sell most of its petrochemical businesses, about 75% of them, and I decided to stay with BP. Quite a lot of my more recent years have been in the biomaterials to fuels areas. So I haven't solely been in petrochemicals. I've been partly in petrochemicals and partly in synthetic fuels, so things like bioethanol. Also, I was involved in a technology which is being commercialized now on converting municipal solid waste to jet fuel. So in hindsight, would I have considered other career options? Well, it's been a very good fit for me. It's really fitted my technical interests and my technical capabilities, but I think as a chemical engineer, I could have settled into any particularly technically demanding careers. So, pharmaceutical specialty chemicals could have worked as well. What am I doing career-wise post-retirement? Well, it's a little bit strange at the moment, as I'm sure you realise. I've got quite a lot of things going on with iChemie through educational accreditation. I'm also involved with the Andrew legacy, which is a chemical engineering professor from who died about 20 years ago, left a big legacy to fund work in catalysis, and I'm part of the committee that think about how to what work should be sponsored in that route. I think if I click answer live, that goes. Oh, done. Okay, I think I've done that one. Putting aside the factor of ISIL, what are the problems if disused plastic could not degrade or takes a long time to degrade? Well, you've simply, it's clearly harmful to the environment. If you get microplastics in the water systems, then they're clearly harmful to wildlife. It's been well demonstrated. Apart from divestments, what practical strategies are we talking are big energies exploring to reduce their carbon footprints? So the big challenge here is creating alternatives that are attractive to the market. This goes back a long way. I think some of the really big energy companies have been in the space of developing alternative energies and materials from alternative feedstocks for a couple of decades, actually. But the problem is, do people buy them? And it's really about the synchronization of the technologies being available, and I think government and society being ready to use them. So I was talking about waste to jet fuel. Well, it depends whether people are happy to pay more for their airline flights, or whether good governments are prepared to legislate to make them do that. So we've seen in the vehicle market, the ground vehicle market, we've seen biodiesel and bioethanol creeping into the fuel supply by legislation. Will we see that in the polymers market? We've seen Coca-Cola, their plant bottle scheme, bringing in some bio-PET. but it's really at the margin at the moment, and it will take something more to get the majority of the drinks industry wanting to go down that route. Right, I've been asked about operator training simulators. What's the next step in the development and use for developing and certifying operators' competence? Well, I would expect they become part of the norm. One of the challenges we have now is if you look at petrochemical plants and oil refinery plants, they're very reliable. Now, very reliable is a really good thing. The problem is, it means that very few operators get a chance to experience a startup. So a steam cracker will be shut down for maintenance work every 4 or 5 years. Now, if it doesn't have an incident that causes it to shut down for that 4 or 5 years, you've only got 1/5 of your operators who've actually experienced doing a startup. Okay, so if you've got a 5-shift system, that means the average operator will experience that once every 25 years. So you have no alternative really to using simulators to get the skill level that you require. So I think it's going to become a very necessary thing. Right, efficiency of plastic waste to energy. Does it produce any toxic materials? It largely depends on what you put into it and what the cleanup is. The efficiency will be broadly similar to any solid fuel based power station, so in the sort of 30 to 50% range, which is normal for either a coal or biomass fired power station. The cleanup, yeah, this is a difficult area because I know that 20, 30, 40 years ago, incinerators created a real issue in society where there was some producing toxic waste, and that put a lot of people against the technologies. I think the technology has improved quite dramatically in that time. Difference between PET and PEF, well, it's a different monomer. The PEF monomer, instead of having a benzene ring, has a furan ring, which is a sort of 5-membered ring with 4 carbons and an oxygen instead of 6 carbons. Gives you very slightly different properties, but there's not a huge amount in it. And one of them has the advantage, the PEF has the advantage that it's more easily made from biofeedstocks. The PET has the advantage that it can be made from a wider range of feedstocks, but at more complexity, and is what the world is using now. So there's always a cost or an impact of changing from one product to another. Main bottlenecks to cost-effective production and commercialization of bio-derived chemicals. I think the biggest thing is that producing the bio feedstocks is more expensive than fossil feedstocks. Fossil feedstocks are, to my mind, still outrageously cheap for what they give you, because nature has spent millions of years gathering together and concentrating up the energy into a small amount of material, whereas biomaterials are more dispersed. So if you think of something like diesel fuel, that contains about 42 megajoules per kilogram of energy. Wood is more like 18. So you've got a much more concentrated energy source, which means that the price is cheaper. With biomaterials also being bulky, there's a larger human cost, and people tend to be expensive compared to machines, and you need more people to produce biofuels and biofeedstocks. The third one is the constraint of land available to grow them, and the potential concern about competition for food land. So those are the sorts of concerns out there. Thank you for the thanks. Right, will existing petrochemical plants be able to be reused in the future if we abruptly decided to solely use environmental options such as biopolymers? If not, what can you do about them? Some parts reusable, some parts not. So I think it's conceivable that you could do partial conversion of a steam cracking plant and a biopolymers plant making conventional polymers from biofeedstock, using a biopyrolysis oil as a feedstock. There would be some significant changes, but there are other technologies which I think you wouldn't be able to use, and you'd essentially have to dismantle, and you'd probably end up sending the steel that the plant was built from for remelting and refabricating in practice. So there's going to be all sorts of different outcomes for different plants. Okay. Ooh, very different tack. What personal attributes would you say helped you succeed in your career as a chemical engineer? I'm quite an unusual chemical engineer because I've stayed very, very close to the technology and very close to the fundamentals throughout my career. And for me, I think the most important thing is regarding all of the knowledge that you come across as being potentially useful. I still have my university notes on the shelf over there in my office, and have referred to them at times in the last few years when I've had to deal with new topics. So the biggest thing I would say is don't treat exams as a hurdle to be got past, ticked off, and the material that went into them forgotten about. Everything is stuff that you need to learn and keep building on, and you carry on learning throughout your career. I've certainly carried on learning hugely throughout mine. And yeah, I think the day you stop learning is the day to give up. Right. Petrochemical plants get inputs from fossil fuel and natural gases. Do you foresee petrochemical plants getting an input from plant agricultural products and cost differences? Yeah, more expensive, not just plant agricultural products, but I think there will be more reuse of waste and more use of either municipal solid waste, domestic waste as a feedstock, and other industrial waste as a feedstock. But it is more expensive, partly because it's more labor intensive, and we need to find ways as a society of incentivizing that to happen rather than using new stuff. You know, the example I'd always cite is if you've got a DVD player and it doesn't work, you can buy a new one for 20 quid. But if you want to get the one you've got fixed, the chances are it will cost you 100. That's our fundamental problem, and it's the same at all levels of goods. What processes other than steam cracking is used to convert raw materials? Well, there are some things that come out of refinery processes directly. So streams containing the aromatics, benzene, toluene, xylenes, they come out of oil refining processes from the catalytic reformer. There's another significant process called steam reforming, where you take natural gas and steam and heat it in a tube, and you get carbon monoxide and hydrogen. And the combination of carbon monoxide and hydrogen is another useful reactive feedstock that goes into quite a range of industries. So the most well-known ones, things like methanol. Methanol can then be made into formaldehyde, which goes into some polymers, but also methanol can go on to make acetic acid, goes into vinyl acetate, goes into a range of polymers and solvents. So there's a huge range of stuff. Will you say that plastic bottles are not actually polymers? And no, they are definitely polymers. This is definitely a polymer. A polymer is something which is made of a lot of small molecules stuck together, okay, chemically reacted together to make larger molecules. So plastic bottle, definitely polymers. It is elastic because its mechanical properties are elastic. Okay. However, if I were to bend it like that and it bent permanently, that's what an elastic. That's a plastic deformation. So I think it's important to take the colloquial use of the word plastic for polymers and ignore it. We want to talk about polymers really for the materials. And I would stick to using, since you're all scientist engineers, stick to using the words plastic and elastic in their physics sense. More and more people talking about biodegradables, biodegradable polymers. In degradation, it decomposes in CO2, and compost level of CO2 is rising. So there has been a school of thought, which is a slightly wacky one, I think, of making large amounts of polymer and burying it underground as a way of sequestering carbon. I'm not sure that really makes sense. I think the issue with biodegradable polymers is not the CO2 it makes, because if you start from a biosource, you're going back to the CO2 it came from. I think the concern is if you go to other less desirable materials in the polymer degradation. So if you took a material and it degraded into potentially toxic chemicals that were liquid, yes, it would kind of disappear into the soil, but you would do harm. The concern is to make biodegradable materials that biodegrade into relatively harmless things. And actually CO2 is harmless in small amounts. We breathe it out at several percent. So it's clearly not that harmful directly. It's clearly it's a concern about the overall atmospheric composition rather than it being toxic. What recycling method is best going forward? We probably have to use a variety of them. We use the simplest one we can. So use mechanical first, use reuse first, mechanical second, and then the various chemical options of increasing complexity as necessary. Done. Is there a method to separate a mixture of different polymers? This is really quite tricky. There are devices which can look at chipped polymer, and so you've got little bits of chip going along a conveyor, and I think an infrared detector can work out what the polymer is, and they've been using things like little air jets to blow the chips of polymer in different directions, but that's always likely to be expensive and complicated and imperfect. So I'm not optimistic that that's going to be a big one to do. Mark, should I keep going? I've noticed it's about 10:58.
No, you're welcome to keep going if you've got time. It's up to you. Right,
there's another 10, 11 open. I'll try and get through those as quickly as I can. Yeah, done that one. Based on experience, is it realistic to expect that someday we'll migrate from petrochemicals to more environmentally friendly options exclusively? Well, I'm slightly wary that there are any holy grails out there in there. I suspect there are quite a lot of applications where plastic is and always will be, or some polymers, I should say. Polymers are and always will be the materials that we use. Whether they're made from fossil fuel feedstocks is more debatable, and the key is whether we can be more circular in how we deal with the waste. So I don't think it'll disappear. Okay, why is engineering important? That's a bit of a big question, isn't it? It's how we make everything. Yeah, I think that's too big a question. I think it's essential. I think it's how we equip a society to live in comfort. Is it possible to develop the biopetrochemicals business without an unsustainable increase in deforestation? Interesting question. I think there is clearly concern around the tropical area. I think there need to be different solutions for different parts of the world. So, for example, it is possible to do sustainable forestry in the northern latitudes. So, think of the Swedish forests are very, very productive and very well managed. Some other feedstocks are grown in other countries. So, the Brazilian bioethanol industry would argue that virtually all of bioethanol, all of sugarcane ethanol, is not grown in areas that compete with the rainforest, but they're in areas which have historically been used for rough grazing. They're more like savanna type lands. It's not an area I'm expert on, so I don't know the answer to that one. Once a petrochemical plant is built, would the design be mostly fixed? The answer is yes, mostly fixed. Nearly every plant I've come across has had little bits of debottleneck or efficiency improvements added to it gradually over the years. But the fundamentals don't normally change very much. Given the fact nowadays green energy, lowering carbon capture campaign are massive globally, also fossil fuel resources keep decreasing, which might impact the supply of petrochemical industry, what might happen? Technology advancement towards environmentally friendly is ongoing. Okay, so there is a quotation which is, I think, attributed to a former executive at Shell, essentially saying that the Stone Age didn't end because we ran out of stones. And I think we're in the same sort of place with the oil industry and the fossil fuel industry. I suspect we are not going to run out of fossil fuels. We're going to stop using them before we run out. So I don't think it's an issue about the feedstock unavailability. I think it's an issue more around society being unwilling to use them because of the consequences. I think then there's an issue of is there enough sustainable material to supply our needs, and that's not totally clear. Would you say plants are carbon neutral? I think they could all be made carbon neutral, but I don't think any of them actually normally are, unless they are deliberately designed to be, because usually there is an energy input. So you may take a biological feedstock to make a biological polymer, but you're still very often putting energy in, and it's a question of what choices you make about that energy. But you've also got all the materials the plant is made out of, the steel and the concrete, and those have quite considerable emissions as well. So there's a lot of different factors in there. So I think it's a journey. I think that's done. Are petrochemical plants today very safe? How is a disaster avoided? I think it's fair to say that very major incidents are pretty rare. And we tend to work to a basis of, well, all big companies work on the basis of we don't want accidents to happen, and we expect you to go home for your day at work in the same shape as you arrived at it. The technical way of viewing that is to say that your risk from an incident at work or from a factory is tiny compared to all of the other risks that we take on board every day. So yes, I think generally plants are pretty safe. In countries like the UK, we have quite constrained zoning, and you are not allowed to build things like homes and offices close to chemical plants. And over the course of my career, I've seen plant control rooms, which used to be sited right in the middle of the plant, so the operators could get out and turn a manual valve quickly. They've all been moved away because of some of the incidents that have happened. And they said, your control room not only has to be blast proof, but needs to be a certain distance away from any of the potential explosion hazards. So the standards that we work to now are quite different from the historic ones. What's the scope of miniaturization of chemical processes in petrochemicals? I think it's very unlikely, simply because these are things which are so uneconomic to make on small scale. I think it's really unlikely. Yeah, I don't see that as being something that will happen. What are the different specializations of chemical engineers in the petrochemical industry? Well, you will have people involved in technology development, which is largely what I've been for most of my career. There will be people involved in plant design, a lot of whom will work for the engineering contracting company. So there's two levels of plant design. There's the concept design of what pieces of technology do we put together to make this process. Then there's the more detailed design of size everything and design everything in detail as you're doing your design project at university. And then there's usually an operations set of roles, which is actually responsibility for day-to-day running of the plant. And which of those suit you really depends on, I think, your personal style and preferences, and what it is you enjoy doing. Some people really get a buzz out of being involved in day-to-day operations, and others find it burdensome. So it's, yeah, horses for courses. Okay, and I'm just going to check the chat. Okay, I think the Q&As, yeah, have picked up everything. Yeah, I'm happy to leave it there. Yeah, well, thank you, everyone. I hope you found that interesting and enjoyable. I just stress that this is just one of many different industries that you as chemical engineering, prospective chemical engineering students could go into. So it's everything from these sorts of petrochemical type materials to the biofuels industry, to food, water, nuclear, pharmaceuticals, specialty chemicals, you name it. There's a huge range of stuff, which I think you've got so many options ahead of you. And I wish you all, I hope you all enjoy doing your chemical engineering degrees, and wish you a successful future. Mark, do I just shut down, or do you take over?
I'll take over now. Thank you, Les. That was a fascinating talk, really great. Yeah, so thank you all for joining. The session will be made available on our faculty Spring into STEM landing page in the next few weeks. If you do have any questions, do feel free to email chemeng.webinars@ucl.ac.uk, and we'll get back to you. And yeah, and also you'll receive a link to our feedback form too. If you can complete that, that'd be fantastic. Okay, well, have a great day, and thanks again for joining. Bye, everyone.